Hi all, welcome back. Today we're going to look at our last section in chapter 10. And this section we're going to look at recursive rules for sequences. So at this point, when we've described our rules for geometric and arithmetic sequences, we describe them explicitly . So if you remember, our rule for an arithmetic sequence was the first term plus n minus 1 times d. And for geometric, our rule was a sub n is equal to the first term times r to the n minus 1. In both of these rules, n is the independent variable where we choose the term number that we're looking for, and then we can solve for that specific term number. Now, there's another way to kind of describe these rules for sequences, and that's with something called a recursive rule. And with a recursive rule, what we're doing is instead of basing this on the term number, it's going to be based on the previous term. So for arithmetic, our next term is equal to the previous term plus that common difference. So notice a sub n minus 1. The n minus 1 is all in the subscript. All this is representing is the previous term. And we'll do some examples here in a moment to help you guys get the handle on this. But it's not super difficult, though the notation looks a little weird. And for a geometric, it's going to be r times the previous term. So again, that n minus 1 is all in the subscript, and all this means is the previous term. Now there's one other thing that we need for both of these. So in both of these situations, we need a starting point, i.e. the value for the first term. So let's look at an example to just kind of help us get the feel for this. So we're just going to write down the first 5 terms for the sequence. So this is all information that would be given to you. Our recursive formula needs our recursive rule, and then it needs something that's going to initialize that recursion. So it needs a starting point. So if we want the first 5 terms, well, we know the first term. To find the second term, so here n is 2. So n minus 1 would be 1. So we need the first term, which we know is negative 4. So negative 4 plus 5 is 1. To do the third term, now n is 3, so n minus 1 is 2. So the third term is the second term, plus 5. Well, we know the second term. We just found that. That's 1. So 1 plus 5 is 6. So the fourth term, so here now n is 4. So 4 minus 1 is 3, so we need the third term plus 5. Well, the third term we just found is 6, and 6 plus 5 is 11. And then the fifth term, well, if n is 5, then n minus 1 is 4, so we need the fourth term plus 5. And we just found the fourth term, that's 11. And we add 5 to that, we get 16. So if I were to write down my sequence then, it would be -4, 1, 6, 11, 16, ... Let's look at a geometric situation. Okay, so again, we're going to write down the first 5 terms. We're given the first term already. So to get the second term, my n is 2. So 2 minus 1 is 1. So the second term is -2 times the first term. And we know the first term is 1. So that's -2. So the third term, so now n is 3. So n minus 1 is 2. So the third term is going to be -2 times the second term. And we know the second term is -2. So we get 4. Now let's do the fourth term. So n is 4. So n minus 1 is 3. So we have -2 times a3. So -2 times the third term, which we just found is 4. So that's -8. And the fifth term is going to be -2 times the previous term, which is 4. So -2 times -8 is 16. So our sequence is 1, -2, 4, -8, and 16. So right away, it should appear to you that it's really easy to do this sort of thing. And in fact, we don't even really need to write out like all of the work we've written out here and here. I was just writing this out to kind of help you illustrate the formula. We know the first term is -4. And because of the form of this, we know it's arithmetic. And we know the d is 5. So I could just be adding 5 each time, because that's really all I'm doing. Similarly, because of the form of this, we know this is geometric, and we know that the r is -2. So really all I'm doing is multiplying by -2 each time to get my next term. That's really all we're doing. So all of this is just me kind of really following the formula and showing you how the formula works, which is great. No problem. However, it's really nice to, in a practical sense, we can just, kind of do this, just by repeated adding or multiplying. Let's look at another example. Okay, so let's say we want to write the recursive rule for this sequence. So the first thing I have to do is determine if this sequence is arithmetic or geometric. So a quick glance here, I can tell right away that it's not arithmetic. So to go from 2 to 14, we added 12. But to go from 14 to 98, we're sure as heck ain't adding 12. So maybe it's geometric. To go from 2 to 14, we multiplied by 7. To go from 14 to 98, we multiplied by 7. And again, maybe you don't know that multiplication times table just right off your head, but it's easy to check that with your calculator. Right? So all I need to do is check to see if 14 times 7 does give me 98. It does. And then we wonder, okay, well, is 98 times 7 also 690 or 686? Sure is. And we still have to check, is 686 times 7 4802? I bet it is. Shocking. It's almost like somebody designed this to work out. So we're convinced at this point this is geometric, and the R is 7. So I'm going to take my recursive form for a geometric sequence. So I need my recursive, or my recursion, and then my initialization. So what we're starting with and how we're doing our building. Okay. Well, in this case, we know R, and we know a sub 1. So we have everything we need. And it's that easy. Let's say that we have this sequence. Okay. So again, first thing I'm going to do is check to see if it's arithmetic or geometric. So right now, it looks like it's arithmetic to me. We're just adding -6 each time. So because we're adding -6, we know the d is equal to -6. So my formula for an arithmetic recursive formula is this. So I need two things. I need a d. Well, I know that. And I need a first term. I know that. So I have everything else that I need. And if you prefer right here, you could write this as just -6. You don't have to write it as plus a negative, but it doesn't make much of a difference to me. So there's that. Okay. What if I wanted you to write the explicit formula as the recursive or vice versa? So first thing we need to do is identify whether this is is arithmetic or geometric. And the way I'm going to do that is by looking at what's going on to my n. So if the n is being multiplied, then it's arithmetic, which is what's going on here. If the n was in the exponent, it would be a geometric, but that's not what's going on here. We have 3 plus 7n. So this is arithmetic. So the formula that I'm going to need requires two things. I need a d, and I need the a sub 1. Well, I shouldn't have done those in yellow, huh? I need a d, and I need an a sub 1. Well, the d is easy to get because the d is just going to be the coefficient on our n. Now the a sub 1 is going to be a little bit more complicated to get, but not so bad. All I'm going to do is I'm going to take my explicit formula and just plug 1 in for n. And there we go. Now I have everything I need. So I have a sub n equals the previous term plus 7, where the first term is 10. That's pretty easy. What if it was a geometric situation? Okay. So right away, first thing I'm going to do is look at the location of n. Since n is in the exponent, I know this is geometric. And the explicit formula for a geometric is the first term times r to the n minus 1. And my recursive formula, I need r, and I need the first term. Well, to find r, oops, I should use something other than yellow. I already used yellow. To find r, I know it's just that. The base of my exponential. Oh, that's easy. And then to find a1, that's just that. It's my coefficient. And so I have everything I need. I don't have to do a thing. So it's going to be 2/5 times the previous term, where the first term is -2. And I'm done. How would we go the other way? Let's say we want to go recursive back to explicit. Okay. So first thing I want to do is identify whether this is arithmetic or geometric. Since we're adding here, I know it's arithmetic. And I can tell that my d is 5, and my first term is -1. Now, if you remember, the explicit formula for an arithmetic was just this. Well, we need the first term, got that. And we need d, got that. So I have everything I need. So if I just plug things in, I have -1 plus n minus 1 times 5. When I distribute that 5 through, I have -1 plus 5n minus 5. And when I combine like terms, I have 5n minus 6. What if we have this one? Okay. So the first thing I want to do is determine whether my recursive formula is explicit. I'm sorry, it's obviously explicit because it's an explicit formula. Is arithmetic or geometric? So the way I can tell that is what's going on between my constant and my previous term. Since the operation there is multiplication, I know this is geometric. So I know that this, the 3, is my r, and my first term is 10. Now if I go back to my explicit formula for a geometric sequence, I know it's this. So the two things I need is my first term, got that, and my r, I got that. So I have everything I need. So all I need to do then is plug them in, and I'm done. Okay. Now there's one final thing that I want to talk about here. And that is looking at recursive formulas. For sequences that are not arithmetic or geometric. So let's look at an example here. So we'll start with a very famous example. This sequence is called the Fibonacci sequence. Those of you that remember from several years ago, or perhaps the movie, there's a very popular book and movie called The Da Vinci Code, where the Fibonacci sequence was a important plot point. This is the Fibonacci sequence. If we look at this sequence, it should be easy to see that it's definitely not arithmetic. To go from 1 to 1, we would have added 1 or added 0. But going from 1 to 2, we'd add 1, so it's not arithmetic because we're not adding the same thing each time. It's not geometric because going from 1 to 1, I'd multiply by 1, but going from 1 to 2, I'd multiply by 2. So it's not geometric either. There must be some other way to represent this. It turns out there is both an explicit and recursive formula. The issue is the explicit formula is quite complicated. However, the recursive rule for this is devastatingly simple. So what this recursive formula works is it's actually based on the previous two terms. That's your hint. So if we look at this, the first term is 1, the second term is 1, the third term is 2. Does anybody notice a relationship between the third term and the previous two terms? Well, 2 is equal to 1 plus 1. Interesting. Let's keep on going. So the fourth term is 3. Notice that 3 is equal to the third term plus the second term. So let's write it this way. That'll help us kind of recognize the pattern that's going on here. Okay, well, let's see going if this pattern holds. The fifth term is 5. Well, 5 is 3 plus 2, so it is the fourth term plus the third term. So it appears to me then my recursive formula is the previous term plus the term before that. However, we're not done. I shouldn't have boxed that because I need to also give the initialization. So because this formula requires not just the previous term, but also the term before that, we actually need 2 starting values, so we need the first 2 terms in our sequence. So I need to give that. So this would be my formula. Let's do another one of those because again, it's not, these ones are a little bit tricky because there's not like just one way to do this, not like there's a given formula. You're just kind of hunting for a pattern. So let's look at this next one. Okay. So again, not sure what's going to be going on here, so let's just kind of go hunting for a pattern. The first term is 1, the second term is 2, the third term is 2, the fourth term is 6, the fifth term is 24. So if I look at this, it appears to me that if I look at, say, 1 times 1, that gives me 1. 2 times 2 gave me 2. 3 times 2 gives me 6. And then 4 times 6 gives me 24. So this is the previous term number times the previous term. So that would be 2 minus 1 times a sub 1, which is 1 times 1. And if I continue that on, that is exactly what's going on. Now this was a tough one because it involved both n and a sub n minus 1, the previous term. And we do need one initialization because we're only depending on one term. So our first term here is 1. So there's my final answer. Now, these are tough. You're going to have to play around a little bit with it. But when you think you have it, all you need to do is check to make sure it generates the terms in your sequence. And if you don't have it, well, you're just going to try again because there's only so many things you can do, right? You can add previous 2 terms, or you might multiply a previous term by a constant and then add it to the other ones. You might be multiplying previous 2 terms. There's lots of possibilities, but there's not that many to kind of play around with and check. But these ones are tough, I admit. So you do just need to kind of play around with them. But that's the general idea. So after this, you should be able to do the assignment for this lecture 4. Good luck, guys.